Okay, so we have 756 here, and we're given this diagram here with a distributed load across the top, and we're supposed to find the internal shear and internal moments and draw the diagrams for those. So kind of the first part of the analysis is to find the reactions at the supports. So we'll proceed by finding the reactions at the supports. So at A, we'll have AY, and then we will also have AX, because that's a pin joint. And since we're on this cylindrical roller here, we'll just have CY at C. We won't have any X direction there. And as you can see from the diagram here, we have no external loadings in the X direction here. So by taking the sum of the forces in the X directions, we just have AX. And through that, we can find out that AX is equal to 0. Okay, now let's look at finding AY and CY. I think to find AY, I think the easiest way to do that is take the sum of the moments around C and set those equal to 0. Counterclockwise is our positive sign convention. So AY is going to create a clockwise moment, which will then be negative. So AY times the distance it's acting away from C is 4 meters. And we have this distributed load here. And the way we can do this is the distance that it acts here is 4 minus 2, so this is 2 here. So if we take 1.5 kilonewtons per meter and multiply it by 2, we get the total load. So that is 3 kilonewtons. And this load is going to create a counterclockwise moment here. Or, I'm sorry, yeah, counterclockwise moment, so it should be positive. So we have 1.5 times 2 is the total load. And how far is that acting away from C? Well, if we combine this whole load, it should be acting right in the middle there, which from C, that is 1 meter. So this distance here is actually 1. So that is 1 meter. So we have times 1 there and set that equal to 0. And from this, solving this equation, we have AY comes out to be 0.75 kilonewtons. Okay, and lastly, we can take the sum of the forces in the y direction and set those equal to 0. And through that, we'll have AY, we'll have our distributed load here, which is 1.5 times 2. And then lastly, CY pointed upwards, set that equal to 0. And solving this equation, plugging in AY there, we have CY is equal to 2.25 kilonewtons. Okay, so we found the reactions now, and now we can get into actually solving for the shear and moment diagrams. Okay, so the way we need to do this is break it into several parts. So we'll define this for x is between 0 and 2 meters. Okay, so for this section, so we'll break this right here. And then the additional section will be from 2 meters to 4 meters. So we'll break it over to here. So let's get those diagrams up, free body diagrams up. I've already drawn them out. Let's move this down. So this is the diagram for x is between 0 and 2. All right. So here we just need to solve this free body diagram. We've cut it so it exposes the internal shear and internal moment here. And this distance is x. All we know is x is between 0 and 2. So let's go ahead and do the sum of the forces in the y direction and set those equal to 0. All right. So we have AY up, and then we have V, our shear, pointed down. And remember that our positive sign convention for shear, when we cut it this way, shear is actually pointed downward here. And we'll set those equal to 0. And if we put in 0.75 for AY, we come out, the shear of V here is equal to 0.75 kilonewtons. And it is constant over this range of 0 to 2. And now we can move on to finding that moment. So finding that moment, setting the sum of the moments equal to 0. So we'll take the moments around x, and x is this point right here. Okay, so x is this point. So we have AY acting a distance, so we have AY, which is going to create a, it will be a clockwise moment, which will be negative AY, times the distance that's acting away is just x. And then we have just our moment here, this is positive, plus m equals 0. And if we put in 0.75 here, we find out that m is equal to 0.75x. So we have our next diagram here, and we have, what we're trying to find is x is between 2 and 4. Okay, so it's the second half of our structure. And even though we're just doing it from 2 to 4, we need to still draw the total left-hand side of this diagram here. And we still have our AY, which is 0.75, our distributed load. And then the way we broke this, we have our positive sign convention for the shear and the moment here, so V and M. All right, so let's solve this by first, let's take the sum of the forces in the y direction. Set those equal to 0. Okay, so we have AY, which is positive, and we know that's 0.75. We have this distributed load here, which is downward, so that's going to be negative, so 1.5. And if this total distance is x here, the length that this distributed load is acting upon is x minus 2. So this distance here over here is x minus 2. So we put in x minus 2 here. And then we also have our downward shear V here. Now rearranging that equation and multiplying this out here, we have, let's see, V is equal to 3.75 minus 1.5 x. Okay. And now we can do the sum of the moments, and we'll do the sum of the moments around x and set those equal to 0 with our positive sign convention. And x is this point right here. And so let's take the moments. We first have AY, which is going to create a clockwise moment, which will be negative. And that distance away is x. And then we have this distributed load here. And we've already found that our distributed load is going to be, it's downward, so it's going to create a counterclockwise moment, which will be positive. So the total of the distributed load is 1.5 times this distance, which is x minus 2. And then the distance that this distributed load acts away is actually halfway. So halfway of this total distributed load, and that distance is here. So what is that? Well, that's x minus 2, and that entire x minus 2 divided by 2. Okay, so that's divided by 2. And then we also have our moment, m, here at the end, and set that equal to 0. And now we can solve for m and multiply these things out. And if we do that, we come out with the moment is then equal to negative 0.75 x squared plus 3.75 x minus 3. So kind of a messy equation there. Okay, so I've drawn the diagram here for the shear, and we have v of x here, and I rewrote our equations that we just solved for that we can use for reference here. So it's 0.75 from 0 to 2, and 3.75 minus 1.5x from 2 to 4. Okay, so from 0 to 2, it's pretty easy. It's just a constant 0.75. So we can just draw a straight line here across to 2. All right, and if we plug in 2 to the second equation, 2 here, and so that's 3.75 minus 2 times 1.5, that is 3.75 minus 3. So we also get 0.75. So that's that point there. Now if we plug in 4 to this equation, so we have 3.75 minus 1.5 times 4, all right, and we need to write down that point, and that comes out to be negative 2.25, which is down here. All right, so that's this point. And we know that this equation is linear, so to do this, we just need to connect these two lines together, or these 2 points together with a line. Let's see if I can do this. Okay. And then at this point, we have an upward CY even of 2.25, so that brings that back to 0. So if we want to fill this in, this is our shear diagram for the loading case that we have. Okay, I've now drawn the moment here, the moment graph or moment diagram, and re-entered our moments that we found from our previous calculations. So from 0 to 2, we have 0.75x, and that's linear, right? When x equals 0, the moment will be 0. That's this point here, this point. And when x equals 2, we will have our moment equal to 1.5. So that's here. Now just connecting those with a line, right there. Okay, so that's 1.5 there. And now going for our equation from 2 to 4 here, that's this equation. This is parabolic, right? And by the negative sign, we can see that it opens downward. And if we plug in 4 into x here and solve this equation, we know if we plug in 4, the moment comes out to 0. So we know the moment at 4 is 0. And we kind of have a parabolic curve. You can use your calculator to graph this, and it looks something like this. Okay, so it's a parabolic curve, and it has a maximum right here. So that maximum, we can find that by taking the derivative of this and setting it equal to 0 and finding what x is. And that maximum occurs when x equals 2.5, and the value, I just had that value up, is 1.69 there. Okay, so that's the maximum that occurs. And so this is our moment diagram. And one other interesting relationship of these two diagrams is if you look at this diagram is actually the derivative of this diagram. So for example, our slope from 0 to 2 is 1.5. Our slope here is 0.75 from 0 to 2. Now that, if we look at the shear diagram, our value is actually 0.75. And our maximum occurs at 2.5 here, x equal to 2.5. Well, what do we see on the shear diagram? Well, we know that's a maximum because on our shear diagram, it intersects the x-axis, and the shear is 0 at that point. So that is the problem 756.